All right, this is chapter 18. We're learning a new type of function today. They're called exponential functions, and we're going to be taking a look at their graphs. And since we're looking at the graphs of functions, that means we're also going to be connecting back to our dear friends, the function transformations. So lots of good stuff. Let's get started. What is an exponential function? Well, it's kind of in the name. It's an exponential function, so the variable is going to be in an exponent, or an index if you prefer that terminology. So here are a few examples. Each of these has a variable in an exponent. They also have some other things going on, but main point, variable in the exponent. Now, just like with linear functions, we need to be comfortable with the multiple representations of an exponential function. So today we'll focus primarily on their graphs, and to some extent we're going to connect those to tables and to equations. We are not going to look today at situations. That's going to be word problems. We're going to see those in the next video. Before we get to graphs, let's just do a little basic function work here. We're dealing with this. F of x is equal to 3 minus 2 to the negative x. What is f of 0? Well, in our heads, the 0 takes the place of the x, so that's going to be 2 to the power of 0, which is 1, and therefore we have 3 minus 1, which is 2. Next one's going to be f of 3, so this is going to be 2 to the negative 3. Now, a negative exponent means that we're going to take the reciprocal and make it positive, so that'll be 1 over 2 to the 3. 2 to the 3 is 8, so now this is 3 minus 1/8, and 3 is equal to 24/8, so our final answer should be 23/8. They gave their answer as a mixed number. I prefer the improper fraction. And for this third one, we're not going to get a numerical answer out of this, but we are going to replace this x with a negative x. So what is that going to make our function? Well, it's just going to be 3 minus 2 to the power of negative x, which is 3 minus 2 to the x. Now we're going to start talking about graphs, and we'll look at a table in here as well. But before we do, I want to point out that when we deal with graphs of exponential functions, the base, which here we're representing with the letter a, the base must always be positive. A has to be bigger than 0, and we're also going to say that a is not equal to 1. Let's think about both of those. Well, first of all, if a is equal to 1, then we have 1 to the power of x. What is 1 to the power of x? It's just 1, right? It's not going to matter what the exponent is. So that's going to result in just a horizontal line. So if a is equal to 1, then we actually don't have an exponential equation, or an exponential function, excuse me. We have a linear function. Boring. What happens when a is negative? Let's say I had negative 1 to the power of x, and that negative 1's got to be in parentheses, by the way. These two are not the same, right? On the right, the x is the exponent for 1, and then we make it negative. On the left, the x is the exponent for negative 1. So, why is this a problem? Well, what happens if x happens to be 1/2? Well, negative 1 to the 1/2. 1/2 is the same as a square root. Remember that rule of exponents? And can we take the square root of a negative? No. So if our base value, if our a is a negative number, then for certain x values, the function won't exist. So we're just not going to deal with that. We're going to insist that we only deal with functions where the base, the a value, is positive and it's not equal to 1. So now we're going to look at an example of one here. So this example is 2 to the power of x. Now, first of all, just look at the table, make sure that these values make sense. When we put in these values for x, we should get out these values for y. And on the right, we have those points plotted. So a few things to notice here. First of all, let's look at those y values in the table. How are they changing? As we move from left to right, our x value is increasing by 1 every time. How is our y value changing? Well, it's multiplying by 2 every time. And the fact that it's times 2, that's no coincidence. It's multiplying by 2 because that's the base of our exponential function. Think back to linear functions. How did their tables change? They increased by the same amount, but it was by addition, or they decreased by subtraction. Here, we're going to deal with multiplication or division. Okay? Now, some things to notice about that graph. Well, for starters, what's the y-intercept? In this case, it's 1. And actually, that's going to be true no matter what that base is. Right? Let's say we had 3 to the power of x. Well, what happens when x is 0? It's still 1. What if I had 1/2 to the power of x? X is 0. It's still 1. So the y-intercept for the basic function a to the power of x, it's always going to be 1. That's something worth remembering. Second thing to notice, the graph is always positive. We can't get a negative number out. We can't raise 2 to a power and get a negative out. The answer has to be positive. That's also something worth remembering. And finally, we notice that as we move out here to the left, these y values are getting smaller and smaller and smaller. It's never quite going to reach 0, though, so we actually have a horizontal asymptote as x approaches negative infinity. As x approaches negative infinity, y approaches 0. As x approaches positive infinity, y approaches positive infinity. That's also something worth remembering. So when we think about the graphs of exponential functions, we want to note, where is the y-intercept? It might not be 1. If the graph is shifted up or down or left or right, then it might not be 1 anymore, but we want to be able to identify that point. We also want to know where the horizontal asymptote is, because every exponential function is going to have one. Now, it's possible for that horizontal asymptote to be relevant as we move out to the right instead of as we move out to the left. So we see here 2 examples where the a value is in between 0 and 1. So if we have, say, 1/2 to the power of x, as we move out to the right, as that x value gets bigger and bigger and bigger, we're multiplying 1/2 by itself many, many times. The y value is getting smaller and smaller and smaller. Whereas when x is a negative number, the y value ends up getting larger. But in all of these cases, we have a y-intercept of exactly 1, and we have a horizontal asymptote at 0. We just need to note whether the graph is approaching that asymptote as we move out to the left or out to the right. All right, now let's start transforming. So we're going to try to sketch a couple of graphs here. 2 to the x plus 3. So forget about the 3 for a second. What do I know about 2 to the x? I know it's going to have a y-intercept of 1. I know it's going to have a horizontal asymptote of 0. But now, the plus 3 is going to move the whole graph up 3 units. So now it's going to have a y-intercept of 1 plus 3, so that's 4, and it's going to have a horizontal asymptote of 3. And that's really all the important information I need to know. I could get a couple of key points by choosing specific values for x. Yes, that's true. But the important points, the y-intercept and that horizontal asymptote, I should be able to figure those out really fast just by thinking about function transformations. How about on the right? Well, here I've got y equals 3 to the x minus 4. So what kind of a function transformation is that? Well, it's 3 to the x. I know what that looks like. It's got a y-intercept of 1 and a horizontal asymptote of 0. But this one is being shifted to the right 4 units. So we can draw that. So I know that I have the point 4, 1, because the y-intercept's being moved over 4 units to rest there. The new y-intercept is going to be when x is 0, we have 3 to the negative 4. That's going to be 1 over 81. I don't know what that is as a decimal off the top of my head. But anyway, there's, again, a quick sketch of 3 to the x minus 4, just thinking in terms of transformations. But you know what? There's actually another way to do this one, if you prefer. So we have 3 to the x minus 4. When I write it like this says horizontal transformation shifted to the right 4 units, and that's true. However, using properties of exponents, this can be rewritten as 3 to the x over 3 to the 4. And 3 to the 4 is just the same as 81. And then I can just rewrite this as 1 over 81 times 3 to the x. And this form tells me that it's been vertically compressed to be 181st as 181th as I don't even know how to say that. But the point is it's way shorter, right? It's like 81 times shorter. That you get what I mean. And when we look at the picture, yeah, you could have viewed this as the dotted line being moved to the right to get to the green line, but it could have also been the dotted line being vertically compressed. Those are both correct answers for this particular transformation. Here are two more. We're going to sketch -4 to the x. Now, the base here is 4. That's a positive number, so we're okay. It's not in parentheses. So 4 to the x, I know what that looks like. It's got a y-intercept of 1 and a horizontal asymptote of 0. But now it's -4 to the x. So that is going to reflect over the x-axis. Now the y-intercept will be at -1. The horizontal asymptote will still be at 0. Okay? Last one. 3 to the -x. Now the negative is attached to the x rather than to the entire function, so this is going to be a horizontal reflection. So it's over the y-axis. Still has a y-intercept of 1, still has a horizontal asymptote of 0, but now it's approaching that asymptote out to the right rather than out to the left. There is, of course, another way to have thought about this one, just like in the last example. So we have 3 to the -x. That's the same thing as 3 to the -1 times -x. And then property of exponents, if we have a product of exponents, we can rewrite it as a power raised to another power. And now 3 to the -1, that's the same thing as 1/3. And remember before, we said that when the base was in between 0 and 1, the graph should be going down, decreasing from left to right. And that's exactly what we see here. It's decreasing from left to right. So back here when we learned about those, we were only concerned with a to the power of x. In the example we just saw, it was 3 to the power of not x, but -x. So that was why we were able to change it to become 1/3 to the power of x again, and we get this decreasing function instead. And what if I wanted to work backwards? What if I wanted to go from a table or a graph and figure out what the function was? This can be a little bit more challenging. In particular, I think a table is annoying because it can be really tough to tell exactly what the horizontal asymptote is. So let's look at a couple of examples, and I'm aware the answers are already on the screen. But let's just take a look at this column here first. Now, look, if I were to give you only these values, so these are the x values, these are the y values, you have no idea what the horizontal asymptote is by looking at this without some like tedious guessing and checking. Eventually, you might be able to work it out, but it's annoying, right? If I continue to scroll up, then we see, oh yeah, the y values here are getting pretty close to 0. Notice that this is scientific notation when well, we see it down here at the bottom. This is 2.32, blah, 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 times 10 to the -8th. So these numbers are essentially 0. So this one seems like it has a horizontal asymptote of 0, which means that my function equation should be just some number to the power of x. I'm not adding or subtracting anything afterwards to move it up or down. What is that number? Well, we just look at these y values. To get from 1 to 9, I'm multiplying by 9. And now I'm multiplying by 9 to get 81. I'm multiplying by 9 to get 729. If you don't see it right away, just use division. 729 divided by 81 is the same as 81 divided by 9 is the same as 9 divided by 1. So it's pretty easy to figure out that the base here is just 9. So my answer is 9 to the power of x. It's a little bit trickier if I have to shift this thing up by 1 unit. So here, again, the answer is going to be 9 to the x plus 1. Again, we see the y values are basically getting closer and closer and closer to 1, so that's cool. But now I can't just use division because 10 divided by 2 is not the same thing as 82 divided by 10. It's not the same thing as 730 divided by 82 and so on. So how can we figure out what the base is here? Well, the way that I would think of it is to get from 2 up to 10, how much of an increase is that? It's an increase of 8. To get from 10 up to 82, that's an increase of 72. And what's 72 divided by 8? That's 9. Or another way you could think of it is you could mentally shift this graph down 1 unit. So you could undo that vertical shift of 1. And we know it's 1 because we've seen up in the table it seems like the horizontal asymptote is 1. And then you'd get friendly y values to work with. And by the way, when you're doing these, there's going to be more than one way to write the answer. So like all 5 of these, for example, are the exact same graph. They just kind of look different. So you might be prompted in the question, give your answer in the form of a to the x plus b, where, and it'll tell you what kind of number a and b are or something like that, for example. How about this one? So we've got a graph in this case. When I look at this, it sure seems as though the horizontal asymptote is at -3. And we're not pulling any tricks on you. If it looks like it's at -3, it's at -3. It's not going to be at -3.02 or some nonsense like that, okay? So my horizontal asymptote is at -3. That means that my equation should be something to the x minus 3. Now, what is that something? Well, let's just look at the y values here. Since my x values are increasing by 1, what are the y values doing? This is an increase of 1. That's an increase of 2. That's an increase of 4. The next one would be an increase of 8. What are those increases multiplying by? They're all multiplying by 2 each time. So my equation here is 2 to the x minus 3. Okay, last one. This one's going to be a little bit tougher. Let's go through it step by step, though. First, the horizontal asymptote appears to be at -1. No tricks. So we should have something to the x minus 1. Well, no tricks about that anyway. I do have a trick coming. Now let's look at the y values to figure out what the base of our exponent should be. So we start up here at -211. We go down by 6. We go down by 3. We go down by 1.5, or let's call that 3 halves. And then we go down by, well, we go down by a half and then another quarter, so we go down by 3/4. You might want to write those out if you can't picture this in your head. We go down by 6, 3, 3 halves, 3/4. What is the ratio that we are multiplying by to get from one number to the next? We're multiplying by 1/2, or we're dividing by 2, right? It's easier to think about that when you're dealing with the whole numbers, right? Going down by 6, then going down by 3. Okay, 6 times 1/2 is equal to 3. So a good guess would be that our function is y equals 1/2 to the power of x minus 1. The problem is that that doesn't work here. And this is where that trick comes in. Because let's think about this. If we try a few values of x, let's say I put in 0. I get, in this function, I get 1/2 to the power of 0. That's 1 minus 1. That's 0. But the point 0, 0 is not on my graph. What we actually have is 0, 2. When I put in x equals 1, I should get 1/2 minus 1, which is going to be -1/2. But instead, I get 1/2. When I put in, let's do a few more. Let's maybe work backwards. When I put in x equals -1, I should get 1/2 to the -1. That's 2 minus 1 is 1. But instead, we get 5. The answer is that there was actually a hidden vertical stretch there. So we actually have a times 1/2 to the power of x. The x is not affecting the a, it's only affecting the 1/2. And we need to figure out what that vertical stretch is. So this is why it's really important that a question tell you what form your answer should be in so that you actually have some way of figuring out like what the function should even look like. Otherwise, you'll be operating in the dark, and it can be really, really tricky that way. So how can we figure out what a is? So all we need to do is pick one point on our graph and put it into this equation for x and y, and it doesn't matter what point we choose. So I have two examples set up here. So in the first one, if we add the 1 over to the other side, then we have a times, well, let's just say it's times 2, since that's 1/2 to the -1, and that's equal to 6. And then from there, I see that a is clearly equal to 3. And down below, if I add the 1 over 1/2 to the power of 0 is just 1, so I get, again, a equals 3 right away. So our equation in this case was 3 times 1/2 to the x minus 1. Okay, that's it for this video. So we covered exponential graphs. All right, the basic exponential function, a to the power of x. It's got a y-intercept of 1, and it's got a horizontal asymptote of 0. If a is bigger than 1, then it's going to increase from left to right. If a is in between 0 and 1, then it's going to decrease from left to right. We should be able to sketch graphs relatively quickly using that information and just thinking in terms of function transformations. And we can come up with the equations from a table or from a graph